Let's continue with the gastrointestinal system explanation. Today we are going to learn about the exocrine pancreas. The learning objectives are: list the composition of pancreatic juice, outline the functions of the various enzymes produced by the pancreas, describe the regulation of pancreatic secretion. So before moving on to the lecture, let's learn some important terms related to this topic. So first one is amylolytic enzymes. Enzymes that help digest starch, glycogen and other carbohydrates except cellulose. Enterokinase, an enzyme that activates trypsinogen to trypsin. It is secreted by the intestinal mucosa when chyme comes in contact with it. Then lipolytic enzymes that help digest fats to fatty acids and glycerol. Then pancreatic acini, sac-like dilations within the exocrine pancreas that secrete pancreatic enzymes. Then pancreatitis, inflammation of the pancreas. Then proteolytic enzymes that help break down proteins into peptides or amino acids. So first major topic is pancreatic secretion. The pancreas, which lies parallel to and beneath the stomach, is a large compound gland, and most of its internal structure is similar to that of the salivary glands. The pancreatic digestive enzyme is secreted by pancreatic acini. A large volume of sodium bicarbonate solution is secreted by the small ductules and larger ducts leading from the acini. The combined product of enzymes and sodium bicarbonate then flows through a long pancreatic duct that normally joins the hepatic duct immediately before it empties into the duodenum through the papilla of Vater, surrounded by the sphincter of Oddi. So when we just try to learn about the composition of pancreatic juice, we can see that pancreatic juice is secreted most abundantly in response to the presence of chyme in the upper portions of the small intestine, and the characteristics of the pancreatic juice are determined to some extent by the types of food in the chyme. The pancreas is also an endocrine gland, and the composition of pancreatic juice can be classified into two majorly: water and solutes. Solutes are once again classified into inorganic components and organic components. Inorganic components, in the sense, there will be sodium bicarbonate and chloride ions, and in organic components part we can see enzymes: proteolytic, lipolytic, amylolytic, trypsin inhibitor kind of enzymes, and mucin. Pancreatic digestive enzymes. Pancreatic secretion contain multiple enzymes for digesting all of the three major types of food: proteins, carbohydrates and fats. It also contains large quantities of bicarbonate ions, which play an important role in the neutralizing ability of the acid of the chyme emptied from the stomach into the duodenum. The most important pancreatic enzyme for digesting proteins are given, which are proteolytic type, amylolytic, lipolytic, then that's it. Some amylolytic and trypsin inhibitor will be there. So proteolytic enzymes are trypsin, chymotrypsin, carboxy polypeptidase. They break down proteins into peptides, split some proteins into individual amino acids, hydrolysis. Then amylolytic enzymes are pancreatic amylases. So they hydrolyze starches, glycogen and other carbohydrates except cellulose to disaccharides and a few trisaccharides. And later there will be lipolytic enzymes. So they are of pancreatic lipase type, or cholesterol esterase, or phospholipases. They perform the function of hydrolysis natural fat into fatty acids and monoglycerides, then hydrolysis of cholesterol esters, then splits fatty acids from phospholipids, etc. So when first synthesized in the pancreatic cells, the proteolytic digestive enzymes are in their enzymatically inactive forms: trypsinogen, chymotrypsinogen, and procarboxy polypeptidase. They become activated only after they are secreted into the intestinal tract. Trypsinogen is activated by an enzyme called enterokinase, which is secreted by the intestinal mucosa when chyme comes in contact with the mucosa. Trypsinogen also can be autocatalytically activated by trypsin that has already been formed from previously secreted trypsinogen. Chymotrypsinogen is activated by trypsin to form chymotrypsin, and procarboxy polypeptidase is activated in a similar manner. Secretion of trypsin inhibitor prevents digestion of the pancreas. It is important that the proteolytic enzymes of the pancreatic juice do not become activated until after they have been secreted into the intestine, because the trypsin and the other enzymes could digest the pancreas itself. So fortunately, the same cells that secrete proteolytic enzymes into the acini of the pancreas simultaneously secrete another substance called trypsin inhibitor. Trypsin inhibitor. This substance, which is formed in the cytoplasm of the glandular cells, prevents activation of trypsin both inside the secretory cells and in the acini and ducts of the pancreas. In addition, because it is trypsin that activates the other pancreatic proteolytic enzymes, trypsin inhibitor prevents activation of the other enzymes as well. When the pancreas becomes severely damaged or when a duct becomes blocked, large quantities of pancreatic secretion becomes pooled in the damaged areas of the pancreas. Under these conditions, the effect of trypsin inhibitor is often overwhelmed, in which case the pancreatic secretions rapidly become activated and can literally digest the entire pancreas within a few hours, giving rise to the condition called acute pancreatitis. This condition is sometimes lethal because of accompanying circulatory shock. Even if it is not lethal, it actually leads to subsequent lifetime of pancreatic insufficiency. So, trypsin inhibitor is very, very important. Next, secretion of bicarbonate ions. Although the enzymes of the pancreatic juice are secreted entirely by the acini of the pancreatic glands, the other two important components of pancreatic juice, bicarbonate ions and water, are secreted mainly by the epithelial cells of the ductules and ducts that lead from the acini. When the pancreas is stimulated to secrete copious quantities of pancreatic juice, the bicarbonate ion concentration can rise to as high as 145 m equivalent per liter, a value above 5 times that of bicarbonate ions in the plasma. This high concentration provides a large quantity of alkali in the pancreatic juice that serves to neutralize the hydrochloric acid emptied into the duodenum from the stomach. The basic steps in the cellular mechanism for secreting sodium bicarbonate solution into the pancreatic ductules and ducts are the following. First step, carbon dioxide diffuse into the interior of the cell from the blood, and under the influence of carbonic anhydrase combines with water to form carbonic acid, H2CO3. The carbonic acid dissociates into bicarbonate ions and hydrogen ions, HCO3 minus and H plus. Additional bicarbonate ions enter the cell through the basolateral membrane by co-transport with sodium ions. The bicarbonate ions are then exchanged from chloride ions by secondary active transport through the luminal border of the cell into the lumen of the duct. The chloride that enters the cell is recycled back into the lumen by special chloride channels. The hydrogen ions formed by dissociation of carbonic acid inside a cell are exchanged for sodium ions through the basolateral membrane of the cell by secondary active transport. Sodium ions also enter the cell by co-transport with bicarbonate across the basolateral membrane. Sodium ions are then transported across the luminar border into the pancreatic duct lumen. The negative voltage of the lumen also pulls the positively charged sodium ions across the tight junctions between the cells. So the overall movement of sodium and bicarbonate ions from the blood into the duct lumen creates an osmotic pressure gradient that causes osmosis of water into the pancreatic duct, thus forming an almost completely isosmotic bicarbonate solution. Then when we just try to learn this, we can see secretion of isoosmotic sodium bicarbonate solution by the pancreatic ducts and ductules, Ca, carbonic anhydrase. What's happening inside this structure? That is, intestinal fluid is there, then pancreatic duct cell will be there, and after that lumen will be there. So Na plus is entering into the pancreatic duct cell from the interstitial fluid. Na plus is entering from the interstitial fluid into the pancreatic duct cell. Then HCO3 minus ions just enter into the pancreatic duct cells from interstitial fluid. CO2 is also similarly entering into the pancreatic duct cell. Na plus is also entering, which we have mentioned earlier, into the pancreatic duct cell. K plus is also entering. Along with that, K plus is leaving the pancreatic duct cell into the interstitial fluid, leaving into the interstitial fluid. Na plus and H2O are just diffusing into the lumen through the pancreatic duct cell from the interstitial fluid. So that is what is happening in case of interstitial fluid. And what is happening in case of pancreatic duct cell? Na plus is entering into that, HCO3 minus is also entering, and along with that H plus is leaving the pancreatic duct cell into the interstitial fluid. Na plus is also leaving along with some entry of Na plus. K plus is also leaving. There is energy change, ATP change involved in that. In case of lumen, Cl minus is entering into the lumen from the pancreatic duct cell. Along with that, Cl minus is also leaving into the pancreatic duct cell. There is a circulation happening. And HCO3 minus is also entering into the lumen. And that HCO3 minus is produced from the CO2 which is present in the interstitial fluid, which transforms into the HCO3 minus in the pancreatic duct cell, and later it is transforming into the HCO3 minus into the lumen. Na plus and H2O are just diffusing into the lumen region. The overall movement of sodium and bicarbonate ions from the blood into the duct lumen creates an osmotic pressure gradient that causes osmosis of water also into the pancreatic duct, thus forming an almost completely isoosmotic bicarbonate solution. So, next topic is regulation of pancreatic secretion. How it's regulated. Basic stimuli that cause pancreatic secretion is very important. So when we try to learn that, we can see that 3 basic stimuli are important in causing pancreatic secretion. Which are they? Acetylcholine, cholecystokinin, then secretin. So acetylcholine, which is secreted from the parasympathetic vagus nerve endings and from other cholinergic nerves in the entire enteric nerve system. Then cholecystokinin, CCK, which is secreted by the duodenal and upper jejunal mucosa when food enters the small intestine. Then secretin, which is also secreted by the duodenal and jejunal mucosa when highly acidic food enters the small intestine. The first two of this stimuli, acetylcholine and CCK, stimulate the acina cells of the pancreas, causing production of large quantities of pancreatic digestive enzymes, but relatively small quantities of water and electrolytes to go with the enzymes. Without the water, most of the enzymes remain temporarily stored in the acini ducts until more fluid secretion comes along to wash them into the duodenum. Secretin, in contrast to the first two basic stimuli, stimulates secretion of the large quantities of water solution of sodium bicarbonate by the pancreatic ductal epithelium. Multiplicative effects of different stimuli. When all the different stimuli of pancreatic secretion occur at once, the total secretion is far greater than the sum of the secretions caused by each one separately. Therefore, the various stimuli are said to multiply or potentiate one another. This pancreatic secretion normally results from the combined effects of multiple basic stimuli, not from one alone. Phases of pancreatic secretion. Pancreatic secretion, as with gastric secretion, occurs in three phases: the cephalic phase, the gastric phase, and the intestinal phase. Their characteristics are described. So first is the cephalic phase. During the cephalic phase of pancreatic secretion, the same nerve signals from the brain that cause secretion of the stomach also cause acetylcholine released by the vagal nerve endings in the pancreas. This signaling causes moderate amounts of enzymes to be secreted into the pancreatic acini, accounting for about 20% of the total secretion of pancreatic enzymes after a meal. However, little of the secretion flows immediately through the pancreatic ducts into the intestine because only a small amount of water and electrolyte are secreted along with the enzymes. Then next phase is the gastric phase. During the gastric phase, the nerve stimulation of enzyme secretion continues, accounting for another 5 to 10% of the pancreatic enzymes secreted after a meal. However, again only small amounts of reach of the duodenum because of the continual lack of significant fluid secretion. Then intestinal phase, that is the next phase. After chyme leaves the stomach and enters the small intestine, pancreatic secretion becomes copious, mainly in response to the hormone secretin. Secretin stimulates copious secretion of bicarbonate ions which neutralize acidic stomach chyme. Secretin is a polypeptide containing 27 amino acids with a molecular weight of about 3,400. It is present in an inactive form like prosecretin in so-called S cells in the mucosa of the duodenum and jejunum. When acid chyme with a pH less than 4.5 to 5.0 enters the duodenum from the stomach, it causes duodenal mucosal release and activation of secretin, which is then absorbed into the blood. The one truly potent constituent of chyme that causes the secretion releases the hydrochloric acid from the stomach. Secretin in turn causes the pancreas to secrete large quantities of fluid containing a high concentration of bicarbonate ion, up to 145 equivalent per liter, but a low concentration of chloride ion. The secretin mechanism is especially important for two reasons. First, secretin begins to be released from the mucosa of the small intestine when the pH of the duodenal contents falls below 4.5 to 5.0, and its release increases greatly as the pH falls to 3.0. This mechanism immediately causes copious secretion of pancreatic juice that contains abundant amounts of sodium bicarbonate. The net result is then the following reaction in duodenum: HCl plus NaHCO3 gives NaCl plus H2CO3. The carbonic acid then immediately dissociates into carbon dioxide and water. The carbon dioxide is absorbed into the blood and expires through the lungs, thus leaving a neutral solution of sodium chloride in the duodenum. In this way, the acid contents that are emptied into the duodenum from the stomach becomes neutralized, and thus further peptic digestive activity by the gastric juices in the duodenum is immediately blocked. Because the mucosa of the small intestine cannot withstand the digestive action of acid gastric juice, this protective mechanism is essential to prevent the development of duodenal ulcers. Then, when we just try to learn the sodium bicarbonate, water, and enzyme secretion by the pancreas caused by the presence of acid HCl, fat, or peptone solution in the duodenum. So we'll be calling this fat as soap. So rate of pancreatic secretion is represented on the y-axis, and HCl, soap, and peptone on the x-axis. So HCl is very high in case of pancreatic secretion is high, that water and NaHCO3 is higher when HCl is present, enzymes are low. But soap, and in case of soap in the sense fat, water and NaHCO3 and enzymes are about equal. Then in case of peptone, enzymes are higher but water and NaHCO3 is lower. Bicarbonate ion secretion by the pancreas provides an appropriate pH for action of the pancreatic digestive enzyme, which function optically in a slightly alkaline or neutral medium at a pH of 7.0 to 8.0. Fortunately, the pH of the sodium bicarbonate secretion averages 8.0. So when I just try to learn the regulation of pancreatic secretion, we can see that there are common bile duct will be there. Acid from stomach releases secretin from wall of duodenum. Fats and amino acids causes release of cholecytokinin (CCK). Then vehicle stimulation releases enzymes into acini. Then secretin causes copious secretion of pancreatic fluid and bicarbonate. Cholecytokinin causes secretion of enzymes. Then secretin and cholecytokinin absorbed into the bloodstream. Cholecytokinin contribute to control of digestive enzyme secretion by the pancreas. The presence of food in the upper small intestine also causes the second hormone CCK, a polypeptide containing 33 amino acids, to be released from yet another group of cells, eye cells, in the mucosa of the duodenum and upper jejunum. This release of CCK results especially from the presence of peptoses and peptones, products of partial protein digestion, and long-chain fatty acids in the chyme coming from the stomach. CCK, like secretin, passes by way of blood to the pancreas, but instead of causing sodium bicarbonate secretion, it mainly causes secretion of much more pancreatic digestive enzymes by the acina cells. This effect is similar to that caused by vagal stimulation, that is even more pronounced, accounting for 70 to 80% of the total secretion of the pancreatic digestive enzyme after a meal. The difference between the pancreatic stimulatory effects of secretin and CCK are very important, and there will be some turning points in that. Like, first one is the intense sodium bicarbonate secretion in response to acid in the duodenum stimulated by secretin. Next, a dual effect in response to a fat or a soap. Then 3, intense digestive enzyme secretion when peptone enter the duodenum stimulated by CCK. So there is general circulation is happening. Secretin will be there. Sympathetic fibers, vagus fibers, parasympathetic, and celiac ganglion is associated with that. Cholecytokinin, serum amylase, and lipase is also associated with that. Pancreas is there. Then secretin induced secretion, fluid and electrolytes will be happening. Then neurogenic or pancreogenzymin induced secretion of enzymes. Trypsinogen is there, enterokinase is happening, present will be there, and secretin is there. Pancreatic acinus, pancreatic fluid, portal vein is associated with that, and amylase, lipase, trypsin, which just influence starch, stomach, and protein. Starch, fat, and protein like dextrins are produced. Fatty acids, maltose, glycerol, peptides, amino acids, peptidases, glucose, maltose, secretin, cholecytokinin, lacteal secretin, cholecytokinin, and then all these are associated with the secretion of pancreatic enzymes.